Welcome to this comprehensive tutorial on CFD analysis of a globe valve. In this video, we'll walk through every step, from understanding the globe valve and simplifying the geometry, to meshing, fluent setup, solution convergence, and results interpretation. Let's dive in. A globe valve is a linear motion valve used to stop, start, and regulate flow. Its name comes from its spherical body shape, with a movable disc-type element and a stationary ring seat in a generally spherical body. Globe valves are widely used in piping systems where flow regulation is required, such as in power plants, chemical processing, HVAC systems, and water treatment industries. They offer better throttling capability compared to gate valves but introduce higher pressure drops. To begin, we import the globe valve CAD model into a modeling tool. First, we simplify the geometry, remove small bolts, logos, and fillets that do not significantly impact the internal fluid flow. Retain only the fluid domain. This includes the inlet, outlet, and the internal flow passages. Next, we perform a volume extract operation. This creates a solid body representing the fluid volume inside the valve. This is the actual region where the CFD solution is computed. After volume extraction, run an interference check to identify and resolve any overlapping or improperly joined bodies. Any leakage or gap between parts can severely affect the mesh quality and solution. Now, open the geometry in meshing. We'll use a surface mesh of appropriate size with inflation layers near the wall to resolve the boundary layer accurately. We will ensure that skewness is less than 0.7 and orthogonal quality is above 0.15. Launch ANSWIS Fluent and read the mesh. Set up the following: solver, pressure-based time, steady-state viscous model, SST-K omega. Boundary conditions are as follows: inlet, set as velocity inlet with magnitude of 1 meter per second. Outlet, set as pressure outlet with 0 PA gauge. Use second-order upwind schemes for momentum and turbulence equations for better accuracy. Initialize from the inlet and set the number of iterations to 1,000. To monitor flow velocity at the outlet, go to Report Definitions, New, Area Weighted Average. Select Variable, Velocity Magnitude. Choose the outlet face as the surface. Name the report definition as Outlet Velocity and enable Report File and Plot for real-time monitoring. Start the simulation. Monitor residuals and outlet velocity. The solution converges in around 1,000 iterations, with residuals dropping below 1 times 10 to the -4th and outlet velocity stabilizing. You can now proceed to post-processing. Let's explore the flow behavior using various plots. Velocity contour. Go to Contours, select Velocity Magnitude, and apply on the mid-plane section. This reveals high-velocity regions near the valve throat and low-speed recirculation zones. Pressure contour. Visualize the static pressure across the valve. Expect a significant pressure drop across the valve seat and throttling zone. Velocity vectors. Display arrows showing flow direction and magnitude. Helps identify regions of recirculation or flow separation. Path lines. Go to Surface Arrow, Streamlines, Arrow, Path lines. Choose Inlet Face as seed source, colored by velocity magnitude. This gives a clear visualization of how fluid moves through the valve internals. That wraps up our CFD analysis of a globe valve. We covered everything from geometry prep to mesh quality, simulation setup, convergence, and results visualization. If you found this tutorial helpful, don't forget to like, subscribe, and comment down below with your questions or suggestions for future videos. Thanks for watching, and happy simulating!